So anyway, all right, on to fast text searching. Here we go.
Hold on to your butts. Yeah, you can go ahead and go to the next slide. So this is all going to be code that I'm going to show. I don't have anything to talk about. So, well, I mean, I'm going to talk through it. So basically imagine like you have a table that contains, say, blog content. So I created a table called blog. Oh, that's not a full create table statement there, but I forgot the name blog, but it is what it is. But it's
Just create some
this
random table out in the ether.
I copy pasted this, so there may be a few errors like that. Anyway, so I created table blog with the primary key, just an incremental ID. The title is the title of the blog. The content is all the text associated with the blog. And presumably, it may be in HTML format. So basically, content is a lot of characters, a lot of data. Titles a little bit shorter, even though I'm not restricting it in general. The blog titles are relatively short.
Right.
And I actually populated this table with about close to 1 million records of data. So there's a fair amount of data in there. And what I did is say we want to search on the title, or we want to search something in the content. So what I was able to do is I was able to create a Btree index. That's your typical standard index on the title. That's what line 6 does. I was able to create an index on that title because the values were short enough. When I tried to create an index on the content, it failed because the Btree index can only have values of a certain length, or it doesn't build, it doesn't work. So I don't know if you could do a pattern ops. Well, that's all for another discussion. Anyway, so you can't really create a Btree index if your text value is too large, but you can do it basically with this. And so now, like any Btree index where you're typically looking for an equality, in line 10, I'm just saying, hey, give me the count of the blog articles where the title is some exact match. The return of the Big Apple or whatever I'm searching for. I just used exact match. There's something in there. And you could, and I'm using explain analyze in it. Now, this is an abbreviated representation of explain analyze because I cut out a lot of the timings for each plan just to see better kind of what's going on. So in this case, line 13, basically it's doing an index only scan. So it's using the index. It's only using the index because it doesn't need to get any data from the heap. So it's just look what's in the index, doing an exact match on what I'm searching for, and it returns all the data. And I tend to not care about planning time too much because that's usually efficient, but I care about the execution time. And you can see it's 0.055 milliseconds, super, super fast. So that's what you expect with a Btree index, looking for an exact value.
Right.
Okay. Well, what if you say, no, but I want to look for any blog posts that have like Apple in the title? And that's what I'm doing in line 21. So I'm using like, you can also use I like, that's the case insensitive version. And I'm putting
I like Apple. I see what you did there.
Yes. And or I like the Big Apple is going to be coming later. Anyway, and you put the percent symbol where you want to kind of replace wild cards for replacing any types of characters. So that's a way for just looking for Apple in them. And you can look at the result here. Now you can see line 28, it's still doing an index only scan. So gee, that should be fast, right? No, because what's actually happening is it says, I got to look through every value of this index and I have no reference to go to. So when I think about indexes and trying to explain what would be slow, what would be fast, think about your use of a book index. If you need to look for an exact value, all right, I'm looking for Apple. First, I'm going to go to A's. Then I go to AP. Then I go APPP. That's what you naturally do. Well, that's exactly how these Btree indexes essentially work to be able to find that value. Now, if you're looking for something in the middle, like if I need to try to find some index value in an index of a book, I have to scan every single page of that index because it's not ordered by Apple. It's ordered by the first character of whatever the blog post is, then the next character, etc. Or sometimes, or you can reverse the order. But basically, I need to now scan the whole index. So what it's doing is it's looking through every value of the index. It's not doing the very efficient scan character by character, but it's looking through everything. Does Apple exist here? No. Apple exist here? No. So it's very inefficient. Now, what later versions of Postgres do, they actually can spawn multiple workers, so you can actually scan the index in parallel. So that's what it's doing here. It's doing a parallel index scan with 2 workers. Now, I could have ramped this up to more workers to get it finished faster. And then the gather stat basically gathers up all the data and finalizes the result to give to you. And as you can tell, the result is 488 milliseconds. So that is it 10,000? I think it's 10,000 times slower.
Yeah. So, I mean, half a second doesn't seem like a long time, but when you're talking about database queries and stuff like
When you're
that,
talking about 1,000 people using your app or more, and each one has to run, that's, yeah.
488 milliseconds is gross.
And this is only 1 million records. I have clients who have, I think one has over 1 trillion records and some tables.
Ouch. So this would take probably at least a second.
If you like this clip and want to watch another one, you can click right here. Or if you want to watch the full video, you can click here.